Hi, I'm Ryan Baker, and this is Big Day in Education. Today we're going to talk about advanced clustering algorithms. Now, there's a lot of algorithms for clustering beyond k-means. The first one I'm going to talk about can be called Gaussian mixture models. It's also often called EM-based clustering or expectation maximization-based clustering. With Gaussian mixture models, you have a centroid and a radius. So each cluster is depicted not just by its center, but by how big it is. And it's fit with the same approach as k-means, with some subtleties on the process for selecting that radius. And it can do fun things like overlapping clusters. If you have centers and radii, you can have overlap. And it can explicitly treat points as outliers, which is a flaw in k-means, as you may remember from earlier in the week. If you remember, there were some points that just never fit all that well to any cluster. And Gaussian mixture models can handle that. So here's an example, and you remember this data set from last week. You got a red cluster, and there's a circle, and a green cluster. And you notice this kind of represents the fact that that lump is not just kind of one lump, but actually has some structure to it. And so there's a green one, a red one, and some stuff that overlaps in the middle. And then there's a purple and an orange, and there are some points that just don't belong to any clusters. If we had a fifth cluster, maybe those 3 points at the bottom could be their own, but we really don't need a cluster for any of those individual other points. Now, a subtlety that's worth mentioning is GMM still assigns every point to a cluster, but has a threshold on what's really considered to be in the cluster. And this is used during model calculation. So, for example, this point up at the top is mathematically in the red cluster. It's closer to any of the others, but it's outside that threshold. It's outside that radius, so it really gets counted as being an outlier. Now, Gaussian mixture models can be assessed with the same approaches as before, distortion, BIC, AIC, plus likelihood, more commonly log likelihood, which is the probability of the data occurring given the model. Or in other words, the probability of each point being there given these centroids and their radii. And it assesses each point's probability given the set of clusters, given the centroids and the radii, and adds it all together. So for instance, for this set of 4 clusters, these are very likely points because they're very close to a centroid. These are less likely points because they're on the edge. They're still relatively likely because they're within the radii, but they're less likely if you really think that data is clumped by these centroids. And finally, this up there is a very unlikely point because it doesn't fit based on this clustering scheme. So the basic idea of this likelihood-based approach is to say, how probable are the points if the data was truly characterized by these centroids and these radii? So Gaussian mixture models have some neat advantages. They can assign points to be part of multiple clusters, they can have overlapping clusters, they can have outliers. There are some disadvantages as well. For one thing, it's much slower to create than k-means. You don't have to just fit centroids, you have to fit radii. And for another thing, they can be overkill for a lot of problems. If you just want to create clusters that you can interpret, think about, and learn from, you might not care whether things are being truly excluded as outliers. Still, they're a good method, and they're useful for a lot of things. Another advanced clustering algorithm is spectral clustering. And here we see an example of spectral clustering. In spectral clustering, we conduct dimensionality reduction, which an example of that was fast correlation-based filtering, but we'll also talk about factor analysis later in the week, and then we conduct clustering. This is in fact extremely analogous to what support vector machines do. And it's mathematically equivalent to doing k-means clustering on a nonlinear dimension-reduced space. If that's gibberish, don't worry about it. Basically, the idea is that spectral clustering collapses your dimensions. Let's say you have 90 dimensions, it collapses them into 4, and then clusters in those 4 dimensions. So why would you want to do spectral clustering? It's because it allows you to find oddly shaped regions of your space that are true clusters, but that across dimensions don't really look like circles or globes or n-dimensional spheres. So it can be very good if you have some sort of weirdnesses in how your data is organized. Hierarchical clustering. In hierarchical clustering, your clusters can contain subclusters. So in other words, let's take this previous example. Let's say we have kind of one overall big pair of clusters, the 2 purple ones. But then within them, we have all these kind of subregions, and we kind of add up the subregions so that, for example, on the right side, you'll see that there are these 2 red that are unified together by the green, but each of the 2 red have 2 subclusters within them. So this allows you to kind of see the structure in your clustering. Another way of looking at this is a dendrogram. So you'll see that 1 and 2 cluster together, and then those 2 cluster together with 3, and 1, 2, and 3 cluster with 4. And then 1, 2, 3, and 4 cluster with 5, 6, 7, 8, and 9. And then finally, 1 through 9 cluster with A, B, C, and D. So this really allows you to see the full structure in your data. It doesn't postulate that there are specific regions that are particularly interesting. That's what k-means or spectral clustering or GMM postulates. It postulates that there's an overall structure and we can see what the breakdowns in that structure, what the groupings in that structure are. The most common type of hierarchical clustering is hierarchical agglomerative clustering, also called HAC clustering, or my personal favorite, HAC clustering. So each data point starts as its own cluster. And then from that set of clusters, you repeatedly try to find the best way to combine any two clusters, whether they have 1 point in them or 70 points. And you do that over and over again, combining the best two clusters, until finally no more clusters can be combined because you only have one group.
So finally today, we'll talk about latent class analysis, which is technically not actually clustering, but I kind of wanted to talk about it in the class, and it's very close to clustering. In latent class analysis, you're doing a type of structural equation modeling that groups data points into a latent variable, which is conceptually really similar to a cluster. It attempts to find data points that are statistically independent of each other when controlling for the group, which is to say that the relationship between the data points in a group is wholly explained by their grouping. And that's in a statistical sense, statistical dependence sense. Why would you want to do this instead of clustering? Well, you can conduct statistical analysis of latent classes, which is to say you can see statistically how well the points fit in their classes, and you can use this method to model changes in the membership of a class over time. But it's got a few drawbacks. First of all, it requires tons and tons of data to be able to find anything. It's very, 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 very slow. It's very slow. Did I mention it's slow? And it tends to find smaller numbers of latent classes than cluster analysis for the same amount of data. That's because it has a higher criterion for putting data points together, which is to say, how close is their statistical dependence. So there's a lot of types of clustering and related methods like LCA. Which one you choose depends on what the data looks like and what kind of patterns you want to find. If you want to find patterns that are very straightforward in an n-dimensional space, k-means might make sense. If you need to collapse down the dimensions, you might want to use spectral clustering. If you want to be able to fit circles and get rid of outliers, you might want to use Gaussian mixture modeling. And if you want to see how the clusters relate to each other, you might want to use hierarchical agglomerative clustering. Lots of options here.
So, there. I've talked about a lot of types of clustering. In the next lecture, I'm actually going to provide some examples of how that's used in EDM research. So, stick around. I'm Ryan Baker. This is Big Data Education. See you next time.